All right. Um, we've been talking about space curves, and now we'll find the length of the space curve. All right, let r of t be a vector-valued function, so that's going to be f of t, g of t, h of t, or f of ti plus g of tj plus h of tk in an interval, as long as t is between a and b. Then the length of that curve, space curve, is going to be the integral from a to b, the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. And this is really easy to show, so I won't do that right here. But notice that's also the integral from a to b of the magnitude of r prime of t. So that's an easy way to think about it. So just for an example, um, let's let r of t be cosine t, sine t, t for t between 0 and pi. And we want to find the length of that curve. So we have the length is the integral from 0 to pi. The square root of f prime is minus sine, but minus sine squared is sine squared. G prime is cosine, and we squared is cosine squared, and t prime is 1, so 1 squared is 1. But we have sine squared plus cosine squared, and that's 2. So actually we're just integrating the square root of 2, which is square root of t. So the answer is square root of 2 pi. Now let's look at what that curve looks like in Maple. Okay, in Maple, we're going to do with plots, suppress the outcome, and we do space curve. Um, let's see, cosine t, sine t, t, t equals 0, pi. And if we box it and turn it around, we can see it looks kind of like a parabola going from corner to corner. And what we're doing is getting the length of this curve, so you can see it better in 3D. And so the length of that curve is a square root of 2 pi. All right, let's now talk about curvature. And curvature measures how quickly a curve C changes direction. So let's start out with a couple of definitions. If C is a smooth curve, then the derivative of R is never 0, except maybe at the endpoints. Then the tangent unit vector, because it'll have length 1, because we're dividing by its length, is t of t and that's going to be r prime of t divided by the length of r prime of t, or its magnitude. And the normal unit vector we'll call n of t, and that's going to be the derivative of the tangent divided by its length. So it's also a unit vector. And this is orthogonal to t. So kind of if we draw a picture, here's a curve C. Here's the tangent unit vector. The normal unit vector always points inside the curve. So n always, like this is concave down, it'll point into the concavity. Okay, then we also have the binormal vector. And that's b of t. And we define that to be t cross n. And this is a unit vector orthogonal to t and n. So in 3 dimensions, we already know what t and n look like. If you form a box, then b is coming like straight out of the box, orthogonal to both of those. And that's called the binormal vector. And r, let's draw r is right here. If this is 0, that's r is a position vector. Okay, let's note some important facts. Um, let s of t, what we're going to try to do is parameterize the curve, and let s of t be the integral from a to t r prime of u du. So s is the arc length from a to t, which is also the integral. Let's do this in 2 dimensions. You could also do 3 dimensions. Since we're in 3 dimensions, we'll do 3 dimensions. Okay, so this is the arc, or s is the arc length function from a to a point t. So if we take the derivative using the fundamental theorem of calculus, let's just f prime squared plus g prime of t squared plus h prime of t squared, which is the magnitude of r prime of t. So I have ds dt is the magnitude of r prime of t. Now what we're trying to do is we want to parameterize the curve with respect to, now from now on I'm just going to write WRT with respect to its arc length. So, and this is because the arc length comes from the shape of the curve. It's not dependent on any coordinate system. So if s is a function from t to t of s, then we can say t is a function from r to r of t of s. And that's what we want. So the curvature, let's go back to curvature. We're going to denote by a kappa, and is the rate of change of the unit tangent vector with respect to the arc length. So that's why we need to define a new function s, which is the arc length function. So we have kappa is dt over ds. Now, using the chain rule, we know dt over ds is dt over dt times dt over ds, and that is t prime of t, or can be written as t prime of t over r prime of t, the magnitude. And that's how we define curvature. So that's how we're going to find it using that formula. There's other formulas too, we'll see. And another one in the book will show you how they get this, so you need to read the book. It's not too hard to figure out. R prime cross R double prime of t over R prime of t cubed is another formula for curvature. And also, if we do k as a function of x, then it's just f double prime of x over the square root of 1 plus f prime of x squared, and all that cubed. So there's three ways to find the curvature, or how fast a curve changes direction. And the last one is if you have a function x. So let's do an example. Let r of t equal t minus t squared, 1 minus t cubed, t at the point 0, 1, 0. Notice that's when t equals 0. So let's go and find a couple things. First, we'll find the derivative. Then we'll find the second derivative. And then we'll find the magnitude of r prime. Okay, and then we're going to cross r and r double prime. So that's this determinant. Okay. And that's going to be I times 6t minus j times 0 plus 2 plus k times minus 6t plus 6t squared. And the magnitude of that is the square root of 6t squared plus 2 squared plus minus 6t plus 6t squared squared, which is 36t squared plus 4 plus 36t squared plus 36t to the fourth minus 72 t cubed. And at t equals 0, that equals the square root of 4, which is 2. And r prime of 0 is square root of 1, which is 1. And then we have r prime cross r double prime over r prime cubed at t equals 0. That's equal to 2 over 1 cubed, which is 2. So the curvature is 2 at the point 0, where t equals 0, so at 0, 1, 0. Okay, let's talk about planes. The plane determined by the normal vector and the binormal vector at a point C is called the normal plane of C at P. It contains all the lines perpendicular to the tangent vector P, and the plane determined by T and N, the tangent vector and the normal vector, at a point C is called the osculating plane of C at P, and it's the closest plane containing the part of the curve nearest P. Okay, so you can look at some of the homework problems that I've done to help you work on your problems.